started. I'm a PhD student under Professor McCoy, and today I'll be talking about the new laboratory we have in NA 203. I'll try to keep the talk pretty brief, and we'll have the lab open for the afternoon from 1 to 3:30 at NA 203. So feel free to eat food, relax down here after we're done, and then stop by for a demo if you want. I'll mention that again at the end. So over the past couple of years, we've been designing, and over the last year, we've built and implemented a new laboratory in the building. It's a multi-physics ship system. The lab has several machinery systems on board a ship, so I'll kind of dive into detail about that. But just to give a brief overview before I get going, I'll talk about why we chose to build this laboratory space, what our objective was, and the anticipated usage of the space itself. And then I'll kind of just give a high-level overview of the system itself through some one-line diagrams and then some example outputs. I'll let you guys enjoy your food and get out of your hair. All right, so the why first. So why do we choose to go through the effort of building and implementing a new lab? We noticed that there's been a lot of work in the autonomous and unmanned marine domain focused on both navigational challenges and navigational challenges, but not and communication and security challenges around the communications. But not much has been done to look at what happens when you remove the operator from the ship and the crew from the ship. And we found that when we took a dive into this from just a stochastic research problem, when you remove the people from the ship, you begin to introduce a reliability problem. They're just simple fixes oftentimes that people are boarding these autonomous vessels for. And it was really evident on the recent trial of the Sea Hunter as it traveled from San Diego to Hawaii. It required 3 instances of boarding, and those were all just for machinery failures. And they were simple failures, fuel filters and diesel generators. But without solving this problem of how we operate these ships successfully with no humans on board, it's not very helpful to have an autonomous ship if you still have to have the hazards of humans on board to maintain the equipment to keep the ship running. So that's kind of what motivated us in this space. We did an initial reliability analysis, and then we looked into what existing technologies were out there. I won't go into detail on the table, but the slides are available if anyone wants to poke at a deeper level. But we looked at what was out there currently, and it seemed like current technologies really showed what was here and now on the system. Like, okay, you have some sort of log or you have some sort of fault right now, but they didn't focus on, okay, in an hour, 2 hours, 4 hours, what the system health projection would be. And so our research is going to focus on how we can project out the future state of the system so we can make knowledgeable actions now about how we operate and maintain this vessel so we don't have failures in mission critical operations. That's just kind of the background of the current research area and the why for the laboratory. I just wanted to give a high level of that, and feel free to jump in with any questions as we go along. The talk won't be too long, so feel free to ask away while we go through as well. So that kind of gives us the why and the background for the laboratory space. So for the purpose and scope, we wanted to inject real world common failures that are causing these autonomous vessels to fail. And we chose to focus on electrical, cooling, fuel, and control systems, and the coupling between these systems. So to start, before we built the lab space itself, we created a Simulink model of the system and kind of tuned that model in. So the model itself showed what type of couplings we wanted to look at and made sure that the dynamics were as we expected for a true shipboard system prior to building the physical system itself. So as you can see here, we have just at a high level an energy generation system, and the electrical dynamics are linked to the cooling system, the mission system, propulsion, and fuel system. And based on the draw energy, the fuel system is reactive to the energy generation system, as well as the cooling system dissipates the waste heat from the generators, as you would see on a ship. So with this, we're able to get the cross couplings of how a degradation in the cooling system would also affect the energy generation system, which would in turn affect your mission and propulsion capabilities. So without these supporting cooling and fuel systems operating properly, you lose capabilities for your mission and propulsion system because your electrical system isn't able to produce as much power as you would need. So then diving into the physical hardware system that we have in the laboratory, I chose to start with the electrical diagram. So in the lab space itself, we start, you can see, we start with a 480 volt input feed. We run that through a delta Y transformer, which steps us down to 208 volts. This also isolates us from the grid and allows us to put imbalanced loads on the system without causing a negative effect on the utility power. With the three-phase input feed, we feed generators. So these generators aren't physical generators burning diesel, because that would both be unsafe and hazardous to have in the building, and doesn't allow us to have the complexity of faults and failures to be able to trigger without just being able to do it once and then having to replace an entire diesel engine. We chose to model a diesel engine with a variable frequency drive fed by the utility power and three-phase induction motor. So we have an electrical three-phase machine with a control loop spinning another electrical three-phase machine that's generating electricity again. If that makes sense. So we take electrical power, run a control loop that emulates the dynamics of a diesel generator and allows us to inject faults, and then that makes mechanical energy like a diesel generator would, or a diesel engine would, and that is coupled to a three-phase generator, which then makes three-phase power like you would see on a shipboard application. So as we load our shipboard buses, we'll see the same dynamics you would on a ship. So when you load the generators, the frequency drops. So we get a normal drip curve, which you wouldn't get if you just plugged your system into a wall. And the three generators themselves feed two main buses. These two main buses are three-phase and at 208 volts as well. The three-phase buses feed two propulsion systems. Those are both three-phase. And then our secondary systems are fed off the secondary switchboards. The secondary switchboards are isolated with the delta Y transformer below. So we take the three-phase power of the main switchboard and we run it through a delta Y transformer. This way, the secondary bus for like running the cooling pumps and fuel pumps, the loads are balanced on the generators themselves. And then similarly, the propulsion loads pull off the main buses, and the propulsion loads are a three-phase induction motor fed with a variable frequency drive, so we can adjust the speed. And we have programmed in a cubic speed to power curve by using by spinning with the three-phase induction motor. We spin a DC generator, and the DC generator is hooked up to a constant resistance load, but we're able to get a cubic loading by adjusting the field voltage, so that as speed increases, the power is exponential. So that's kind of just like a high level with the electrical drawing of the systems we have. And I'll kind of show some pictures and more of the fun stuff now. Yeah.
Where was it when you came onto the project? And then I see in progress, there's more stuff. Like where was it when you joined, and how much further, how many more things are you trying to install? Like, or right now, do you want to start people testing things?
Yeah, so that's a good question. So when I started, we started with an empty room. NA 203 was complete, well, it was less than completely empty. There were some shelves on the walls that we took down. And over the summer, the first summer, we had facilities hang up plywood boards on the wall, and we installed all the equipment and wired it ourselves. So since I've been on the project, we've designed the system and built it and implemented it, and we've just usually like commissioned it with the control system. So we kind of started with a blank room, and I think there's a lot of more work that we want to see happen. But this is just the kind of first steps, and my PhD thesis will be the first one to utilize the space. So lots of cool stuff to come. So it would be really awesome if more students got interested in it and did projects within the lab space. I think there's a lot more that can be done with it that I'll even begin to touch on. And we have a few other students working on the project as well. Ethan is an undergraduate student working on modeling the fuel system dynamics. So yeah, it would be great if anyone wants to get involved, please reach out. So next I'll just run through kind of some pictures of the laboratory space and talk about it a bit more in detail. As you can see here, this is the electrical system we talked about at the beginning. These are our emulated diesel generators. We have 3 of them. They feed the 2 main switchboards you see on the left. So one of them feeds one switchboard, and we can also couple the switchboards together, and 2 of them feed the other switchboard. On the left here, you can see the 3-phase induction motors fed by the wall. So those are taking electrical power, making mechanical power, making electrical power again. So coming out of here, we have that shipboard dynamical electrical power from these 3 generators. The next imagery that goes with the electrical system. And then for the propulsion system, like initially mentioned from the electrical 1-line diagram, you can see the 2 variable frequency drives on the wall on the left that feed the 2 3-phase induction motors closest to the wall, which make mechanical shaft power. And then to emulate that propulsion propeller loading, we have these 2 field motors. They're hooked up to enclosed in the cabinet constant resistor. And then with our control system and the power supplies within this box, we load the field to get that cubic loading curve. So as the speed increases, the field voltage increases power output. And for the mission system, we have 2 programmable load banks, gratefully donated by Professor Jingsun. These load banks allow us to do various loads, constant resistance or pulse loads or ramp loads. Some of the examples, you can see an example of the pulse load on the bottom left in the graph. So the 2 3-phase the power supplies are fed by the 3-phase switchboards. They make the power, which then feed the 2 programmable loads. So each of the load banks is hooked up to one of the main switchboards. So these allow us to put any type of load we would want to emulate onto our 2 buses. And then next, for a detailed view of the cooling system, 1-line diagram on the left, we have 2 parallel and redundant pathways there. So we can simulate faults and failures with redundancy. To simulate leaks, we have movable valves that we can trigger open to create leak pathways. And then we have proportional valves that we can throttle to create a clogging profile like you would see from from a filter clogging or pipe flow. So then these two pumps flow water over two heaters in parallel, and the heaters are loaded based on the efficiency and using a lookup table. So based on however much the electrical generator is loaded, the efficiency multiplied by the efficiency of the generator and a constant factor for the waste heat loss through the cooling jackets, we then place a load on into the heating system. So based on how much electrical power you're using, you need more power, there's more of a waste heat you have to dissipate with the cooling system. So this way we can review the coupled dynamics. So you might have a fault or failure in the cooling system that affects the cooling system flow. Maybe it affects the amount of waste heat you're able to dissipate, and it's going to cause a thermal effect runaway, or maybe it's just going to cause a slightly greater heat rise over the emulated cooled engine. And then based on the effects, we can then set limits in the system to ensure it stays within a healthy operating state. And then in the bottom graph, you can just see an example of a leak being triggered at about 90 seconds. The flow sharply drops through path 1 due to a lower resistance leak pathway. And then this is the overview of the fuel system. The fuel system is set up similarly to the cooling system. It has 2 parallel paths to implement redundancy and emulates the injection of 2 high pressure fuel systems. So we have a low pressure supply system you can see on the left. This is mimicking the pumping of the fuel from tanks up to the high pressure fuel rail or up to the diesel engine system, and then the high pressure simulates the on the engine fuel dynamic systems that you can see boxed in red, 2 parallel paths. And Ethan is the undergrad student currently working on implementing the dynamics of fuel injection. And then this is just a visual of the fuel and cooling system. On the right, you can see the cooling system. We have 2 65-gallon tanks on the ground. The left tank we call the ocean tank. The fuel pumps pull from this tank and run through those 2 parallel paths we talked about, and across these 2 heaters in the boxes. The variable frequency drives on the table provide the waste heat to dissipate the heaters, and then the flow goes back into the tank on the right, which is waste heat. So then we can see the temperature rise across the system. And then similarly on the left, you can see the 2 parallel paths for the fuel system. The low pressure pumps for the fuel system are on the ground. And they feed the 2 high pressure pumps that are table. And then you can see the smaller boxes represent the valves that we can simulate injection and clog. And then for our control system, we utilize 2 compact Rios. We have them linked over a local network with just 1 computer and both controllers. And the controllers use primarily analog signals to both receive data for data acquisition and controls, and send signals for controlling the various equipment within the laboratory space. So there's a total of about 120 signals that we have to work with, which is exciting. Anyways. So then just a quick visual of that system. You can see the first controller we installed in the middle image. It's within a donated cabinet from GE. The space is really nice to be able to pull out all those signals. But then we noticed that one Cerio wasn't going to cut it for all the things we wanted to do. So we ended up installing a second controller for some of the more critical controls on the generators themselves. And then you can see the main control station on the far left with the human interface page up on the big screen there. And then the workstation to sit and make the controls from. And of course, the emergency stop on the walls. And then this is just a larger overview of the space and all the systems put together. Yeah, we started from an empty room around this time last year, and we finally built and installed all the systems, and now we're really excited to start taking data and run some prognostics on the data and do some research with the systems. So I know that was a pretty quick run through, and I'm really happy to entertain any questions you guys have and walk back through the slides. And I'll also be in the lab for the afternoon with Professor McCoy if you guys want to stop by for a quick demo. Thank you so much for listening.
You have some sponsored money to help fund the creation of the lab, right? Can you speak to what the deliverable is or what they're hoping that you learn from what you're doing?
Yeah, do you wanna?
Go ahead. Sure.
Okay, so the lab was built as part of a donation from the Office of Naval Research. We're very grateful for the donation. We got $100,000 to put together the system, as well as funding for one PhD student, which is myself. So the goal is to be able to have some sort of prognostics, so we understand what the current health of the system is, and we can project out what the health might be, say 10 or 30 days later. And by knowing that health, was to either be able to allocate what type of mission it should do based on its capabilities, or make maintenance decisions. So maybe it's able to do one type of mission but not the other, so you can send it on that, or maybe it needs to be sent back to maintenance prior to taking out the mission, so you ensure that failures don't happen during critical operation. Yeah, go ahead.
You plan on modeling machineries like engines and all that? Like now I saw like fuel and cooling systems.
Yeah, so the diesel generators do model the dynamic response of a true diesel generator, and we can also model a gas turbine.
Like balls.
Yeah. So that's the kind of the nice part about using the variable frequency drive coupled to the induction motor. We're trying to emulate the mechanical energy and profile you would see based on the fault state. That makes sense? Yeah. Go ahead.
How hot does it get in there?
How hot does it get? What do you want to see and how long do you run it for? Luckily, we have a pretty good HVAC. I think we have the suction side. I'm not sure who's the lucky winner of the return from our room, but usually stays pretty cool. Yeah, go ahead.
You could advertise our project to reduce the heat.
Yeah, if anyone's looking to make a DC to DC converter, that would be great. We need a buck boost converter so we can take our variable output that we're just burning as heat from the propulsion supply or from the propulsion system and put it back onto the grid.
We had an ink student work on it over the summer, and he had a prototype built, but he wasn't ready to go to full scale. Still an open project.
Yeah, go ahead.
So how is your lab similar or different to other labs across the US? Because I worked with Gibbs and Cox over the summer, and I believe they had a similar lab, and like we're planning on visiting you guys maybe. I don't know, like if the concepts are very similar, like if they're like, I don't know.
You want me to take that one?
Yeah, sure, go ahead.
So
That'd be great.
I've not seen what Gibbs and Cox has. Yes, they had talked about coming to visit us, but they haven't followed up on that. As far as university labs, Navy has funded a number of schools to put together electric chip research. Basically laboratories, the largest of which is at Florida State University. And they have a system that's at the tens of megawatt scale. And the ones at kilowatt scale here. So I mean, their lab is bigger than our entire building. But it takes over $1 million a year to keep that running. You also have South Carolina, Purdue, Virginia Tech, that have some hardware setups. MIT is also in that consortium, but they don't have any hardware. What's unique about this one is we're the first ones that actually put together the electrical system with other systems that you would find on the ship. So we have a cooling system, fuel system. We might add other systems later if we get additional funding. So that's what's unique about this system.
We have a first here.
Thank you for your presentation. So good. How do you make sure you capture any mode of failure? And if you don't, did you identify, for example, the most common mode of failure?
Yeah, so my master's work was looking into what the most common modes of failures were, and we noticed that they were common failures, and oftentimes with the supply systems. So like just the cooling and fuel system, like a lot of the failures that they were boarding for instance, like that C-Hunter example was just like simple clogging of filters. So we're choosing just to start with the common modes of failures and the most prominent modes of failures, and focus on those challenges. And then once we overcome that obstacle, diving into the suite of more detailed failures. But I think there's a lot that can be done with just predicting the common modes of failures that are occurring right now. Pretty simple failures, but it's just a completely different environment you're asking for. Before, you're used to sailors being on board and being able to change things at a whim's notice, and that was just the way of doing business. But now you're operating in environment completely absent from support and physical touch.
Thank you.
You were first.
What's the most difficult or frustrating part of like setting this whole thing up? Like what part did you hate the most?
Yeah, that's a great question. Just with the number of signals and trying to get them all together was very challenging. Nothing's that complex on its own, but then once you put it together, there's like 100 different ways it could go together, and just allocating resources properly is really challenging. So with the control system, you have 2 FPGA planes, a bunch of modules, 2 serial processors that are running in Linux, and then a host computer. And trying to decide what should go where and why is like, there's a million ways you could do it. One way might be better than the other, but you just need it to work, and like moving things around, was really challenging. So yeah, that was definitely the biggest frustration of just having everything built together, knowing how you want to emulate everything, but not being able to get the signals to process fast enough. Just been a lot of trouble trying to see data, record data, and control with the same data. Was really tricky.
Yeah, we hate LabVIEW too.
Yeah. You hate it, but like DSpace is just as evil, and like it's hard to want to do all 3 things at once. I think in real like commercial systems, maybe you're not recording like 1,000 times a second or trying to see it in one-off. LabVIEW is not so fun.
Shout out to your EEC students over the summer.
Yeah, I did have 2. We do have 2 great EEC students that worked in the lab all summer and are still working with us, and the students, and I know the audience as well, without the student support, it wouldn't have been possible. It's a village, and it takes people working hard on something and finding what doesn't work. So very grateful for all this support from the department. Yeah, go ahead.
Do you think the Navy's ever gonna have universities look into steam turboelectric propulsion, or are they gonna leave that up to the Department of Naval Reactors or the shipbuilders?
Oh, I'm not even gonna try to answer that one.
You know what I mean?
Yeah, of course.
The only place they use steam propulsion anymore for Navy ships is on nuclear vessels. So any work they do there, they're gonna, Naval Reactors is in charge of that, and they're gonna hire Benison Capital to do that work. Those are the two. They're government-owned, contractor operated, kind of wholly owned subsidiaries of Naval Reactors that do various bits of research work. And because of classification issues, I doubt Naval Reactors would ever send work out to universities.
Oh, okay. Thanks.
Anyone else? All right, well, we tried to keep it short so you guys can stop by after you enjoy your food and come see a tour. I think it's more fun to see it in person than it is to hear me ramble all day on slides. So if you have 5 minutes or 10 minutes, feel free to come stop by. It's opposite side of the building upstairs, NA 203. I'll be around till 3:30 just with the door open, just running the systems and kind of showing what we can do. Beth McCoy will be there as well.